Great, thanks very much, and good morning, everybody. It's great to be back at a Spark Summit and be visiting Amsterdam. So I hope you all have a great conference. So I'm Nick Pentreath. I'm ML Nick on Twitter and GitHub. I work at IBM as a principal engineer within a team called Code, which is the Center for Open Source Data and AI Technologies. I focus on machine learning and AI applications. I've been involved with the Apache Spark project for a long time, committer and PMC member on that project. More recently doing a lot of deep learning applications. I wrote a book, Machine Learning with Spark. It's a little bit out of date now, but hopefully in the future there'll be a newer version of it. And I travel around the world speaking at various conferences, meetups around data and AI topics. So before we start on the main topic, a little bit about the Code team. So when I joined this team a few years ago at IBM, it was called at that point the Spark Technology Center and was mostly focused around the Apache Spark project and the kind of surrounding ecosystem within the data and AI space. And since then, the team has expanded its focus to encompass the end-to-end enterprise AI lifecycle. We focus on open source technologies and projects. There are around over 30 open source developers, and that covers the Python data science stack. Deep learning, obviously still Apache Spark is a big component of that, as well as a few more recent projects coming out of IBM research for model training, explainability, fairness, robustness, and the Model Asset exchange, which I'll talk a little bit about during this talk. So today we'll start with a brief overview of continuous integration and deployment, then move on to an overview of machine learning and the machine learning workflow, and then look at how the CI/CD situation is a little bit different for machine learning workflows and applications versus standard software. And then I'll talk about what we're doing in the Model Asset Exchange and some of the ways that we are looking at CI/CD for the set of use cases that we have, and then wrap up. So continuous integration and deployment is all around testing ultimately that our application is doing what it's supposed to do. So this is kind of a simplified application. We might have a web app that's talking to users with some back-end services. Some of them may be under our own control, so our own services. Some of them might be remote with data, speaking to data stores and so on. And ultimately, we want to test that if we're going to make changes to our code, to our application, changes to the way we integrate with our services or the back-end services or remote services, we want to be sure that any change made doesn't break our code, doesn't break our application. So we start with the kind of smallest unit, really, of testing, which is typically testing within a single application or a single piece of software, right down to testing individual methods, and then moving on to testing how changes made actually affect the integration between these services. So integration testing, are we impacting the way that our application is speaking to a backend service, or the way that our backend service might be speaking to some remote service. And then finally we have the sort of end-to-end testing, and typically this will be something that we might want to do pre-deploying changes to the application, so sort of acceptance testing, making sure that we haven't broken anything in the end-to-end flow, as well as once an application is out in the wild, we want to continue to do monitoring and post-deployment testing to ensure that nothing is going wrong after we may have passed some tests in pre-deploy phase. So the development process typically looks like this. We have source control, the code that we have under our control, typically sitting in Git or whatever the case may be. And we have external dependencies, and we pull them together to build the software. We then move on to testing. And once we're happy that change is not going to break anything, we merge it and we move on to the deployment phase. So to start with, if we don't have any CI/CD in place, typically all of these are manual processes. So hopefully we start with some tests, but we may start with no tests. I mean, first of all, we have to obviously make sure we have them in place and we write them. But the entire process is manual. We trigger a build, we run the tests. Once we're happy, we may merge that change, and then we go through a manual deployment process. The idea behind continuous integration is to start automating this pipeline. So CI will typically be focused on the code change itself. So typically this will be working in feature branches, pull requests, and so on that we're kind of familiar with from modern software development practices. But we want to try and automate this build and test phase as a starting point. So that's typically will be done. There's myriad tools for doing this. Typically on GitHub, whether it's public GitHub or private, you'll be testing pull request branches, feature branches, using some tool that of which are many, Circle CI, Travis, etc., etc. But typically, with your standard continuous integration, you still have this manual merge and deploy. And the idea behind continuous deployment is to try and further this automation. Typically, merging is still going to be, obviously a manual process, because this is something where you want to do a lot of code review, and you want someone to actually make a decision to go ahead and merge that. But if all of the testing infrastructure is in place, including the end-to-end acceptance testing, then once that change is merged, it can go through the final acceptance testing for pre-deploy, automate the deployment, and then you have the post-deploy tests in place. So the only manual step here should be the human intervention of saying, okay, we're going to go ahead and merge this change. And where are those changes coming from? Typically, in standard software, we have control over our own code, the code that we're writing, and typically the internal dependencies we may have. So we may be depending on some internal service. As a team deploying code, we may not actually have control over that service itself, but we have some level of control because it's in the same organization. Then, of course, we have third-party dependencies over which we have no control, or very limited control. In some cases, it might be an open source project, and we can at least potentially have some impact on that, or go and see what the changes are. So that's standard, and a very kind of high-level overview of standard continuous integration deployment for normal software. So before we go into the details of the aspects of machine learning for that, we'll just cover the machine learning workflow briefly. So the standard perception of machine learning, may be that you just simply take some data, you apply machine learning or deep learning, and you're done, right? You can take your bonus and go home. But the reality is that this piece is actually, or the simplified process is actually a really complex workflow, and it covers teams and use cases. So we start with data, and that's typically the domain of data engineers. Some of it's arriving in real time in a streaming fashion. A lot of it is in historical batch data. It's sitting in all kinds of different locations. Then that data is moved into the typical data science workflow, where we ingest it into that workflow, and the data scientist will be doing data visualization, feature processing and engineering, transformation, getting that data into a form that is actually usable in the machine learning model. Then comes the model training phase, which is actually a sort of small part of this whole process. And that's all about the model selection and evaluation. And once the best model is for the particular use case is trained, then we need to go and deploy it. There's no point in having a trained model if it's not actually going to get deployed into the real world and have some impact. And once it's deployed, that deployment phase is typically crossing a team boundary into kind of machine learning engineers and production engineers. Once it's deployed, we have to continue to monitor and evaluate it, and it's making predictions on new data, and potentially impacting its own data. So you've got this feedback loop from that live system and that live model into the beginning of the workflow, which is your data and your ingest. So it's spanning all these different teams. So to build any data science application or machine learning, deep learning powered application, we actually have to take all of these different teams and use cases into account, as well as tools. Every data science team will have all the different kinds of tools that they like to use. And in fact, on most teams that are above 1 or 2 people, or 3, maybe 3, you're going to hit most of these, in fact. So on a medium to large team, you'll have all the different kinds of frameworks, you'll have all the different kinds of data formats, locations, schemas changing over time. You've got to worry about data integrity and security at the ingest phase. And you're going to be using all the different kinds of tools, machine learning libraries, languages. And finally, this entire workflow, although it is very complicated and it is a critical part of a deep learning or machine learning application, is still a really small piece of the puzzle. So I really like this, by now fairly old diagram, but I think as pertinent as it ever was. And it comes from the Google paper, Hidden Technical Debt for Machine Learning Systems. And I really like the way it shows that this machine learning code that we're talking about here is a really small part of the entire application. So when you think about this concept of integration testing, you can see here that that's probably one of the most critical pieces of testing for deep learning applications. Because even if our machine learning code is correct, if it's not integrating into all of these other components, it's not going to work. So when we talk about a model, and think about what are we deploying and what do we need to test here, most of the time the common perception is the model is just a trained algorithm. It's a machine learning algorithm with a set of weights. But in fact, there's a whole bunch of steps that come before that. So starting with raw data, you can't typically just feed that into a machine learning model. So the data comes in all kinds of formats. Some of it's raw text, unstructured. So there's categorical features, categorical variables. We can't just feed it directly into the machine learning model typically. So we need to transform the data, extract those features, potentially do pre-processing steps, and then train the model. And if we don't apply exactly the same phases in that, or steps in that pipeline at prediction as we do at training, we're going to end up with garbage in, garbage out. So we need to apply exactly the same steps before making a prediction, and we need to ensure that they're consistent and that there's no model skew between training and between prediction. So again, the common perception of deep learning is that it often gets rid of some of these issues, right? It can just work on raw data. You just throw an image in and you get a prediction out, for example. But in reality, deep learning pipelines are as complex, if not more so, in terms of all of these additional pre-processing as well as post-processing steps that are required. So this is just an example for images, but it works. It applies just as well to, say, text or any other data input. So for, let's say, object detection or image classification, we start with an input image, but we can't just feed that raw image into our TensorFlow model. We have to do quite a lot of pre-processing before that. We have to decode the image at a minimum, typically resize it and normalize it, and potentially convert different types of formats, memory layouts, and so on, to make sure that it's in the correct form that TensorFlow or PyTorch can understand, which is typically a set of input tensors. And that's typically going to be done in some sort of image processing library, Pillow, OpenCV, TensorFlow, and so on. And then even once we've got the prediction, we still have to do some post-processing that comes out of that. So we get a tensor out from the prediction phase, the inference phase. And that's typically going to be a tensor of predicted probabilities. But we need to transform that into a human and or machine-readable format so that we can integrate it into the rest of our application or microservice stack. So as you saw, the machine learning code, the deep learning model itself, is only a small piece of this whole thing. And typically, there's going to be some format for interchange, whether it's JSON or protocol buffers, it doesn't really matter. But we need to take that typically tensor and transform it into a set of labels and probabilities, for example, in this case, and do some sorting and so on. And this is typically custom Python code. So at the end, we get out our prediction. So this deep learning pipeline is as complex as any other machine learning pipeline with respect to pre-processing and post-processing. So we need to ensure that we test not just the model, but these phases that come before. And this is probably even more critical for deep learning because some of these small sort of issues in any of these steps can actually be really difficult to detect, but can lead to catastrophic results. So, for example, differences in the way that the image is decoded, depending on the library. If you switch from using one at training to one at prediction, you can actually have a completely different result in terms of that predicted probability and class, but the input image would look exactly the same to you. So all of this needs to be tested at each level, both at the individual method, the step, and the entire pipeline. So the key here is that we're deploying and testing not just this model, but the pipeline, the entire workflow. So we need to take into account the data transform, feature extraction, pre-processing, the model itself, post-prediction, and we need to even think about the data, which we'll get to a little bit later. So that's a little bit about the machine learning workflow and some of the intricacies involved. So how does this now fit in with what we talked about before, our continuous integration and deployment? So the key is how does this workflow make that whole process different? And if we think about the sources of change coming in a typical deep learning application, just in the pipeline alone, we have everything that comes from the software side as well as these additional considerations. So changes come from our code, internal and external dependencies, but they also come from at least 3 additional sources. The first is the data itself, the second is the model, and the third is time. So for the data, some of the issues that we need to think about are how do changes in the data, how is that going to effectively impact the model? So typically, if you're talking about your standard tabular data in machine learning or deep learning, then any change in data schema can have a big impact on the model performance. So taking away features, for example, adding features, changing the way a featured column is defined, changing a type, any of these things, if they're not correctly versioned and documented, and if they're not correctly integrated into the pipeline, can have a big impact. So it's not enough to just test based on some static set of data or to make assumptions about the data coming in. We need to use as much real data as possible. The data types involved in deep learning in particular are quite different though from your typical tabular data. So a lot of the workflows may be well set up for pulling data from a database as part of a process. But when you're talking about huge amounts of images, video, audio, the size becomes quite a big issue. So for a deep learning model, or any machine learning model, you want to train on enough data to ensure that you're going to get the correct result. So if you're making changes that are for a production model, you're going to probably want to train on all the data. But if you're making incremental changes as part of a development process, you don't want to have to train on the entire data set. It takes a lot of time and resources. So you need to think about how to handle the size in that workflow. So for the full production workflow, if you're deploying a change of the model to production, you want to scale that up. But for incremental changes in development, in the development cycle or locally, you want to be able to train on a small enough subset, but still have that, be sure that result or how the model is changing is still going to be correct and is going to have enough accuracy and so on. So in the same way that we've got to worry about size of the data, the size of the models becomes quite a big issue. So deep learning models, in particular for images, for video, for text, can be really, really large. They can be many, many gigabytes. And this means that in some cases, you might hit up against limitations with tool sets. So we found, for example, Travis has a certain limitation on how big a container can be, what are the memory limitations. So that you need to take that into account. Resources, obviously, training a full model can take, for these large image models and text models can take days, sometimes weeks. So if yes, of course, if you are updating a model for, as I mentioned earlier, for pushing that model to production, and this is the new version of language translation or whatever the case may be, then yes, you need to train that entire model, and you need to do it on for days or weeks. But if you're trying to have a rapid development process and kind of iterative life cycle, then you need to try and scale down the model that you're building so that it doesn't take too long. Otherwise, you have this huge blocker in the process. You have to take hardware into account, so it's not enough to just run tests on a laptop or maybe run on a little Jenkins box somewhere, but you typically are going to have to ensure that changes to the model work still on all the hardware targets that are important. So CPU, GPU for training, for deployment will be mobile and edge. Then the next point here is that you need to bridge all of these different frameworks. So there's a bit of a framework zoo on the right-hand side here, and you can see just a few of them that are out there, and languages and toolkits. And typically you need to work with all of them with some combination. And then finally, the state of the art is changing very rapidly. So it can be very difficult to integrate updates to whatever the state of the art model is. And if that's coming from research code, that needs to be integrated into your pipeline. So we've talked a little bit about considerations for data and considerations for the model. And the other thing I mentioned is how things change over time. So another difference between traditional software and machine learning based applications is that for traditional software, you can effectively, in most cases, assume that there's a determinism, right? It's deterministic. If you make a change to your code, you can expect what the outcome is going to be, and you can test for all of those outcomes, and you can typically test for the edge cases. You may not always get them, but you can actually reason through all of those. And you know that once you've tested it, you can deploy it with confidence that it's going to stay the same. So as long as the inputs are not changing and you've covered all the edge cases, you're not going to have a problem. But the issue for machine learning is that it's not deterministic, it's probabilistic, effectively, right? So you don't know how the data itself is going to change over time. A model was trained on a specific set of data, typically historical, and the data distribution often will change over time. So in this case, we need to think really carefully about adding the post-deploy testing, and in particular, this sort of ongoing post-deploy monitoring and testing to the CD pipeline. Because it's not enough to just assume that everything is static and then everything will remain working. So monitoring for machine learning systems covers kind of three pillars. So the first is the traditional software monitoring, which is what we may do for as post-deployment testing for any software system. So think about latency, throughput, resource usage, and testing that things work, that our API works when we've deployed it, and so on. But we also have this second pillar of the model performance metrics, and this is typically what we're going to be working with earlier in the process when we are working through that the data science kind of sub-workflow of training models. So there we've got things like accuracy, prediction error, area under curve, RMSE, whatever the case may be. So if you're deploying an image classifier, you might worry about accuracy and AUC. But in production, once you've deployed that, that's going to potentially change over time. So you need to continually monitor what the accuracy and the AUC is. Because as time evolves, the underlying data may actually change, the process may change, the user behavior may change, and the actual predictive performance of that model may decline. And typically if it comes below some sort of threshold, you're going to want to retrain it. And then the third pillar is business metrics. So there's no point in just deploying a model and we know that it's really accurate. But if it doesn't have a positive impact on the business, it's not really useful. So think about recommender systems. How much revenue are they adding to the business? Fraud detection. How much fraud are we detecting? What is our cost saving? And of course, if you're a user-facing business, how are we influencing user behavior? And the key here is that these business metrics are not, directly tied to the model performance metrics. So just because our model is really accurate doesn't mean that it's good at impacting the business. So again, from recommenders, for example, you typically have a metric that might be the reconstruction error of a matrix factorization, RMSE for ratings prediction, or something like a ranking metric. And that gives you some indication of how well you're doing at predicting user behavior, but you still don't know exactly what the outcome is going to be. So you really need to in production, monitor the business metric and do A/B testing and so on. And similarly for model performance, if your business metric is declining, but your model performance is the same, then again, that is another thing that you need to monitor and potentially retrain or look at model updates. So that entire kind of post-deploy monitoring feedback loop is more critical in machine learning applications than anything else. And I mentioned feedback loops. Effectively, once a model is in production, and in particular models that are user-facing, like recommender systems, such as chatbots and so on, they may actually be changing the user behavior or having an impact on the user behavior. So we need to, this needs to be monitored quite carefully to ensure that we're not getting stuck into some sort of feedback loop. And then the final kind of unique thing about machine learning and deep learning and AI systems is that there's some other aspects that we need to think about. In particular, fairness, transparency, and security. So this is quite a topical issue at the moment, with a lot in the news about bias in machine learning systems. So it's not enough to just think about the business metric or the accuracy and how well is our machine learning model predicting things. But we need to take into account, is there an inherent bias in the system? And we need to, if possible, mitigate that. So either working on the data side by adjusting data, or on the model side by adjusting the model. And this needs to be part of our testing pipeline. So both at training time, we need to ensure that we're taking this into account, because if we haven't thought about it and if we're not monitoring it and checking a metric and testing for it, then it's not going to be solved. Nothing's going to change. But it also needs to be done in production in the real system and the live system. So in the same way that we had the monitoring and feedback for accuracy and business metrics, we need to start looking at bias, explainability. And then another aspect of machine learning systems that's different is that once they're out in production, they may be susceptible to attack. So this is kind of adversarial issues. Now, of course, all software systems are subject potentially to attack and hacking and so on. But there's an additional element which goes beyond the standard software security, which is adversarial robustness. And can an attacker, without having to hack the security and get into the network or have any other kind of attack, can they actually impact the way that the model is performing? And typical examples are in image classification, for example. You can have an attack that can, with a change in the image that is imperceptible to a human, you can change the prediction of the image. So in some cases it seems quite benign. I mean, you go from something being a panda being predicted to be an ambulance. But in other cases, a stop sign can be predicted to be a speed limit sign. So in the case of self-driving cars, this has critical implications for not just application security, but human security. So this is another aspect that needs to be taken into account and monitored both at training time and on a continuous basis in the live system. So to cover these, there are many toolkits out there. I just want to mention the three that we've worked on at Coday and IBM Research. So they are the AI Explainability 360 Toolkit, AI Fairness 360, and Adversarial Robustness Toolbox. So this covers defense and attacks for adversarial robustness, for deep learning, and now most recently including kind of non-deep learning models, so not just images but also text predominantly. AI Fairness 360 is a toolkit for monitoring and mitigating bias, both on the data and the model side, and explainability seeks to kind of address this black box issue of explainable models and ensuring that we can trust the predictions and actually explain why a model, in particular deep learning, but not limited to that, is doing what it is predicting what it is predicting. Okay, so those are some of the challenges for deep learning kind of testing and deployment pipelines and integration pipelines. I'll just very briefly mention the Model Asset Exchange and some of the work that we're doing in, to try and enhance the CI/CD side of that. So the Model Asset Exchange is a project that we launched about a year and a half ago, and it seeks to be a kind of one-stop shop, so to speak, but it's free, so it's not a shop, I guess. One-stop resource for state-of-the-art deep learning models, free and open source. So it covers a wide variety of domains, including images, text, video, audio. Critically, we seek to remove the barriers for entry for application developers and data scientists to find and use these models. So we go and we vet and test the code and the IP associated with them. Everything is free and open and released under open source licenses. And we have both trained and trainable versions. So for the pre-trained versions, which are kind of deployable assets on Max, we effectively are taking either training models ourselves or taking best-of-breed pre-trained models from the research community. And the deployable asset on Max effectively becomes the pre-trained model as well as the I/O processing, so that kind of pre-processing that we saw before, and then the post-processing, as well as a Swagger specification or open API specification for the REST API. And we package that up as a Docker container hosted on Docker Hub, and you can easily deploy it with a line of code. So the REST API, for example, looks like this. You have a standardized REST endpoints for accessing model metadata and labels, for example, as well as making predictions. And as you can see here, this is an example of a particular model, but we have a couple of ways to explore this model. So everything's hosted on GitHub and it's open, but we also have the try the API, try the web app, and there's a few others. And what we do is we host these resources on our own Kubernetes cluster. So we have the model service and the web app. So these are demo resources, but it still means that we have to take into account the entire kind of CI/CD pipeline that we mentioned before. So from GitHub code changes on GitHub to model changes on our cloud object storage, which is where the model files are hosted, we then need to deploy to these hosted services, API and web app. And on the Trainable side, we're effectively making it really easy to combine all of those aspects of data model and compute and expertise with a standardized set of scripts and wrappers that allow you to train the model on your own data on our Watson machine learning service. So at the moment, we have automated deployment of each Docker container. So effectively, once code changes are made on GitHub, we integrate that with Docker Hub. The latest changes are pulled to Docker Hub, built, and published as a container. And if we have a new version release of the container, then we have a Jenkins job that deploys that to our Kubernetes cluster for long-running instances. There are many tools that you can use for CI. But on GitHub, we're currently using a combination of Travis for the GitHub repositories, as well as for more complex workflows, we're using Jenkins. So, as mentioned, Travis may have some issues for particularly large models where you run out of memory running the tests in the container. So the way around that is to either use Jenkins, or we've been exploring GitHub Actions, which seem to have higher resource settings and allowances, and that seems to have been working better. So we've kind of just started to touch the surface of trying to automate the CD pipeline for our setups and all our Model Asset Exchange models. So at the moment, we've got the CI side of things that's working pretty well. we've got the continuous deployment to the container service, which is working quite well. And we've got trainable model testing, which at the moment is typically working on a fairly small subset of the data. Some of the things that we haven't really gotten to yet are scaling up that trainable model testing. So ways to ensure that the models, when they're retrained, are going to be have the correct accuracy and so on. Okay. So yeah, in conclusion, just a few points that for continuous deployment of deep learning applications and machine learning applications, we have to think about full machine learning pipelines and not just models. So we can't just test the TensorFlow model, whatever it is, but we have to test all the pre-processing code, post-processing code, inference code that comes with it. We need to take into account where the changes are coming from, in addition to normal software. So changes in data, schemas over time, changes coming from the model and the entire pipeline, how that varies over time in production, as well as additional metrics and aspects like fairness, explainability, and transparency. And then finally, I mentioned sort of containers and Kubernetes clusters that we're working on, and that probably most machine learning projects and applications that are being deployed in production are using. So some things that we're starting to look at and that may be really interesting, but didn't have enough time to go through today, is looking at using Kubeflow or MLflow or some of the other higher level frameworks to try and take care of that pipeline aspect. So being able to use one framework and one sort of deployment target for testing that entire pipeline instead of having to have multiple different ones. And trying to do your CI/CD pipelines using Kubernetes as well, so that you can use Kube for everything from development to deployment to testing the full delivery pipeline. So Tekton is one project there that may be interesting. Okay, thank you very much for your time. I encourage you to go and check out codea.org, which is our website, and list all the projects that we work on together with IBM Research and the Codea team. And if you want to find out more about the Model Asset Exchange in particular, you can go and check out the ibm.biz/model exchange. I'm happy to chat about anything related to this talk or the projects offline. And I think we've got a few minutes for questions.
Thanks, Nick. We have a couple minutes. If anyone has a couple questions, if we do run over, I'd ask that maybe try to catch Nick outside while we set up for our next talk. But if anyone has a question about this.
Hi, thanks for the presentation. I was wondering for unit testing, at which stage of the experimentation or through production do we require to test, and do we test a pipeline, pre-processing, post-processing pipeline and model? When do we start?
Yeah, I mean, it's a good question because it comes back down to the development velocity and the way that you iterate. I mean, ultimately, if you're talking about standard software, you would say that CI means that you test every time you push, right? And that you should be able to kick off as much of the full pipeline as possible at that phase. So not necessarily the full pre-acceptance and pre-deploy testing, but certainly your full CI pipeline. So it's not always possible, but I would recommend trying to do as much of it as possible. So on our Max assets, for example, every push to GitHub naturally, because of the way that they're set up, it's a self-contained pipeline and incorporates the pre-processing steps, the inference, and the post-processing. Naturally, the actual test itself builds the Docker container and does tests with inputs through the entire pipeline to get the output. And then, that's in addition to the kind of standard unit tests of methods or smaller functionality. So I think for the ML pipeline, in as much as it's possible, I would say trying to test the full pipeline every time you're making a change or push the code. Of course, it's not always possible when you're doing local development and and fast iteration. But ultimately, when you get to making larger changes and pushing it to production, you want to then scale it up. We're doing small tests on very small inputs typically when we're making small changes to the GitHub repo that is the model asset. But when you're training models on custom data, then you're going to want to kick off a full training and a full test run. So doing evaluation and ensuring that all your metrics on a large enough test set are up to standard and so on.
All right, folks, I'm afraid we're out of time. If you could please fill out the survey. There's a gentleman who would like to ask you a question, Nick, maybe right outside after the session. Thank you for joining us, and enjoy the rest of the summit.